All right, so now that we have the general law, the Biot-Savart, that we can use to calculate any magnetic field, let's try an example. We're going to try an example of applying this actually in the wire trig form here. And to make this interesting, what I want to try to do is see if whether or not, as my example, I can take my favorite long line, a long current carrying wire, the one thing for which we do know the result. I'm going to then use that as an example for Biot-Savart and see if we can't recover exactly the result that we know has to be the correct answer. So this then is going to become my example. So the example is going to be an infinite or a long current carrying wire. So the setup for this is going to be just what we're very familiar with. I'm going to have my long wire. He'll be carrying his current here off to the left, like I always like to do. I'm going to set up some coordinate axes. So there's going to be a y-axis going upwards. And I'm going to be interested in the magnetic field at this point y, I will call it, up above the wire. The wire, of course, is oriented along the x-axis, so let me give you my coordinate system. Standard coordinate system I hat in this direction, j hat, or y, is vertical, and then k hat, to make a nice right-handed coordinate system, will be out of the page in the usual fashion. And my job then is to compute the magnetic field B here at location y. What will that be? Now, here's the procedure then that we are going to want to follow, right? We're going to begin with Biot-Savart. So I'm going to write that down. I'm going to want the magnetic field, and I'm going to try to compute it using this standard form for the law. So let me slide. I'm just going to copy this form down here and begin working with it. So just below here, let me copy down. I know then that the magnetic field is going to be given by mu naught over 4 pi. Those are the basic prefactors. Integral I dl along my wire, cross then the trig form r hat over r squared. So, to perform the integral then in this form, I clearly want to divide up my system into a whole tiny, a whole series of chunks. I'm going to divide my chunks up. It's going to be a little bit counterintuitive, but to make the integral work out nicely, I might as well just chunk myself in the normal direction of the positive x-axis. I'll draw a little arrow here to remind me which way x points. So I'm going to make little chunks like this. Each chunk will be at a location x, and he will have a width dx. And that little chunk here then, according to my formula here, will make a contribution to B, where I'm going to need to know, oh, that is not coming out particularly straight. Let me try again here. I'm going to come down like this here. That will be the vector that points from my source of my field to the location where I want my field. And so if I continue this vector out like so, that will be the r hat vector that I'm dealing with. And now my job is to evaluate this integral. So let us proceed then. So we can, of course, bring out our prefactors. We've got mu naught times I divided by 4 pi. I have, those are the prefactors. I have my integral. I should then be very careful to work through my cross product. Before I work through the cross product, I don't want to forget my factor of 1 over r squared. So let me just factor that out first, 1 over r squared. And then for the cross product, I have the magnitude of dl times the magnitude of r hat times the sine of the angle between them. And now let's look at these quantities one at a time. The magnitude of dl, the length of my little chunk here, well, that length of that chunk is clearly just dx. The magnitude of r hat, well, r hat is just a unit vector, so the magnitude of that is 1. Now, sine theta is going to be a little bit tricky. We have to be very careful that we know the directions of our various vectors. dl, remember, always points in the direction of the current. So dl actually is going to be pointing this way because it carries that sense of direction of the current. dl points that way. R hat, as I had indicated to you here, up above, points up that way. Now, to get the angle between two vectors, of course, what we always do is we parallel transport one of the vectors so that they both line up at their base. So the r hat vector would be here, and the angle theta that we're discussing then has to be this angle in the diagram, like so. Now that angle is something I think that we understand, right? We've got this nice right triangle here. The sine of theta would be the opposite side divided by the hypotenuse. So the opposite side is, of course, y. The hypotenuse then is going to be square root of, by the Pythagorean theorem, this side I know is x, because that gives me the coordinate of my point. This side is y, so it's going to be root x squared plus y squared. The last piece that's missing, of course, because this is a cross product, and we should have remembered it from the beginning, is I wrote the magnitude. I neglected to write the direction of the cross product. So I'll put some parentheses here. We're going to need some kind of a vector. Now, cross product again is between dl and r. dl points this way, so I need to orient my right hand with my fingers along the direction off to the left. I then need to rotate that hand until it's convenient to curl my fingers towards the towards this r hat direction. Remember, this is r hat. This is just a copy, this here vector, of the r hat vector there. Now, sometimes, particularly when the vectors in a cross product are not at right angles, it can get a little tricky mentally to do this properly. So here's something that I always do, particularly when they are not at right angles. I remember the basics, which is that the two vectors I'm dealing with here clearly span a plane, and the cross product is perpendicular to that plane. The right-hand rule just is to tell you which of the two perpendicular directions. So if I think of these two vectors, they are both in the plane of the page. So the answer has to be perpendicular to the plane of the page. So the answer is either going to be up or down. Now if I take the fingers of my right hand and orient them along DL, right? And then I have two choices. I need my thumb either oriented up or down. If I orient my thumb up, for instance, and have my fingers along this DL, if I do that properly with my right hand with the thumb up, I'll be, right? I'm going to be bending my fingers backwards to curl them towards DX. That can't be the right direction. So I rotate my hand, keeping my fingers off to the left, my thumb downward, and then it's very natural to curl my fingers towards DX. So the result of this cross product is a vector that is into the page, or in other words, it's in the opposite of the k hat direction because k hat is out of the page. So it's going to be minus k hat direction. All right, very good. So now I think we are prepared to do a little bit of mathematics. So what I have then are all of my various prefactors. I've got mu naught I divided by 4 pi. I then have the integral. And now very clearly, x is my variable. Y is constant because I'm always at a constant distance from the wire. X is my variable. I've got a dx. I'm clearly integrating with respect to x. And the range of x then is from minus infinity to infinity. The next factor I have is this 1 over r squared. Now, if I'm going to integrate with respect to x, everything has to be in terms of x. R, recall, is defined as the distance between the source of the field here and the point where I'm observing the field. so that r is in fact my hypotenuse again. So I'm going to hold back on writing that because I have r squared here and another hypotenuse down there. The next term I have is dx. That can go on the end of the line. 1 is just 1. Minus k hat also goes on the end. That just gives me my direction. So what I'm left with then is my numerator y divided by that hypotenuse, which was x squared plus y squared square root, right? So that's just the hypotenuse, but then I had the hypotenuse squared, so the total is hypotenuse cubed. Hypotenuse is square root, so to cube it, first I cube it, but then I have to remember I'm taking the square root. So I have a 3/2 power. I'm then integrating dx, so that takes care of my dx factor. So I've been very careful. I've done my prefactors. Check. I did my 1 over r squared and my denominator there. Check. 1 doesn't matter. Check. I just wrote my dx here. Check. I got the y factor. Check. I can see here. And then all that was left over is that it goes into the page. Minus k hat. Check. All right. So notice I like this quite a bit because it's in the right direction. I know my magnetic field is in the minus k hat. I see my mu naught I. I like that. I don't like the 4 pi. It's supposed to be 2 pi, and it's supposed to be 2 pi divided by x. I don't quite see how x is coming out of this yet, but we're getting close now. Or it should be divided by y. So we just have to compute this integral, and then we will be finished. So let's look at this integral. This clearly is crying out for some kind of a trig substitution. And if you go ahead and carry through the trig substitution, for reasons of time I'll spare you, but you're going to do a trig substitution. And what you want to say is that x is going to equal y times the tan of theta. You want to do that because then you'll have y squared plus y squared tan squared theta. That'll turn into a y squared secant squared theta, which will turn out very nicely for us. So if you make that substitution, what you're going to find is that this whole integral just has the value of 2 divided by y. And that's perfect then, because when we put the whole package together, we end up with mu naught times I, right? 2 on top and 4 pi on the bottom gives me 2 pi on the bottom. That's starting to sound good. There's a y on the bottom, and then there's the minus k hat direction. And that, in fact, is exactly the magnetic field from our long wire. Here, I'll just put a box around this, and I'll go up and show you. And then we can wrap up our discussion, because if we go all the way back to where we first tried to come up with the Biot-Savart law, our magnetic field was mu naught I divided by 2 pi r. In that case, r was the distance to the wire. And what we have is exactly that. Mu naught I divided by 2 pi y, and y in this case is in fact the distance to the wire. So we have done our first example with Biot-Savart, and it's completely consistent with the ideas we used actually to guess at this law in the first place.